Welcome to Bode plot examples, Lawrence Tech's Mechatronics class, EME 3214. The previous set of slides I covered the theory of Bode plots. Here we're just going to literally pound out some examples of creating Bode plots from straight line approximations, first order, second order, things like that. So we'll go through the process and step by step, and I'll try to explain it all and draw it and subject you to my bad artwork. But hopefully we'll get somewhere. Okay, our first example is a very simple one, a first order real pole. The two things we need to know about first order system is what is the steady state gain and where is the corner frequency when we draw a Bode plot. So I'm going to rewrite my transfer function just a little bit. I'm going to say g of j omega, substituting j omega for s, so we work in the frequency domain, equals 10 over 1 over 5 j omega plus 1. Now I put it in that format because now the 1 over 5 becomes our time constant tau, and our corner frequency or break frequency on our plot here, omega b equals 1 over tau. Okay, so that makes our omega b equal to 5, and the other thing we want is our steady state gain, and that the steady state gain, essentially that's our k up here, so k equals 10, but for the Bode plot we want it in decibels, and that's equal to 20 dB. So our rules for plotting is we start at our steady state point and draw a straight line. Well, let me put in my break frequency of 5 hertz. 1, 2, 3, 4, 5. That'll be here, omega b, and I will start here with a at the 20 dB point, because that's my steady state gain. I will go to my straight line to my break frequency 5, draw that across, and then for my straight line approximation, since there's a single pole, I'm going to roll off at 20 dBs per decade. So I go from 5 to 2, 3, 4, 5. There's my decade, and 20 dB down gets me to that point. So I can connect those, and that's my straight line approximation of the magnitude. Yeah, I can improve it a little bit even by eyeball, because I know that at this break frequency, my actual magnitude is going to be down by 3 dB. So if I come down about somewhere about there, and I can kind of just eyeball fudge it here. So the actual transfer function will look a little closer to that. Okay? That's the magnitude plot. The phase plot, the rule is we have our break frequency, we have corner frequencies at 1/10 and 10 times that frequency. So at 1, 2, 3, 4, 5, this is 0.1 omega b, and 1 right there is, I'll put it down here, better place. Right there is 10 omega b, and we start out for a single pole, we start out with 0 degrees of phase lag. We cross through our break frequency at 45 degrees, and we hit 90 degrees at our 10 point, and I'll try to draw as straight as I can. So that goes like that, and then we flatten out at -90 degrees of phase beyond that point. So that's a first order pole. It's pretty straightforward, doesn't take much effort to draw. First order zeros, it's much the same thing, okay? I'm going to rewrite this just a little bit. I'll say that G of j omega equals 0.7 times 1j omega plus 1. And I wrote it that way because now my gain of 0.7 is approximately 3 dB. And I have a, my break frequency here is 1 over 1 omega b equals 1. So that's my break frequency here at 10 to the 0, 10 to 0. I'm at minus 3 dB, so I'll start out about there and go to there. Just like before, it's a straight line from low frequency into our break point for the magnitude. And then because this is a pole and not a zero, our slope is, 20 dBs per decade up instead of down. So I'll go up one more decade and I'll go to 17 here, connect that point, and just keep on going. Okay, so that's our magnitude. The phase plot is essentially the same thing, except we start at 0 and at 1/10 of our break frequency right there, and we end up at 90 at 10 times that break frequency. We cross through 45, but it's a positive phase, so it's going to look like this, and if that graph were extended, that would be horizontal there. And that's the first order real zero, which is just a mirror image of the first order real pole reflected about the 0 dB or the 0 degrees of phase angle point. And as we have talked about, you can look at the effects of each pole and each zero separately and just add them up. So let's go to the next one, where we have a lead compensator, where I have a pole down here, I have a zero up here, and I can calculate, I can draw the effect of the pole, I can draw the effect of the zero, and I can graphically add those up. Let me rewrite this a little bit. G of j omega, I'm sorry. G of j omega equals, and I'm going to write this as 35 times s plus 1 over s plus 5, except I wanted to do those as j omegas. And if I divide through by 5, I get 35 over 5 times j omega plus 1 over 1/5 j omega plus 1. So my steady state gain is this 35 over 5, or 7, which is equal to, in decibels, 17 dB, and I have a pole at minus 5, and I have a zero at 1. Okay? Or I could look at here, my tau is 1/5, and that gives me a break frequency of 5. It pretty much works out the same way, whether I look at the pole directly or if I work out the tau. I just got to be careful to get the right steady state gain. And if you remember, going way back, the final value theorem in Laplace domain, as time approaches infinity, s approaches 0, right? So as time goes to infinity, these terms go to 0, and I'm left with my steady state gain there of 35 over 5 if it was a step response. And you get the same gain in frequency domain. Okay, well, because at low frequencies, essentially that is just the response to a simple input. So we can, the 0 is at a This is omega B is there, and at 5, 2, 3, omega B for the pole is right there. Let's do the magnitude part first. I start out at 0 dB, I go to there, so my 0, and let me get the right point here, my 0 goes like that, my pole comes along right on top of it, and that goes all the way to here, right there, and rolls off at 20 dB per decade, so that goes to that point right there. And I'll draw the two phase effects first, and then we'll go then we'll combine them. So my phase at 1/10 of the break frequency for the 0 is here, and I start out at 0, and it would have been constant up to here, and I go to 10 times the break frequency and plus 90 because it's a 0, and it goes through 45 here at the break frequency for the 0. So that's my phase of the 0. The phase of my pole there, it should go through minus 45 right there at the break frequency, and it should go through this point here. I'm going to erase that one, and it should go through this point here. That's actually over one more. Can't count. So the 0 pole is going to roll off like that. Now, if I'm clever, I can change the ink color without, we'll go to this color. Hopefully somebody's not red-blue colorblind. So if I graphically add these, my final response over here on the magnitude, obviously it's 0, because 0 plus 0 is 0. 0 plus this rising line is going to track that. And then at this point, right here, now I have one line increasing at 20 dB per decade and one line decreasing at 20 dB per decade. So when you add those together, you just end up with a horizontal line right through there. In the phase domain, it's much the same thing. Here we're increasing up to that point. Now I have the one term increasing, the other term decreasing. That gives me approximately a flat line somewhere out to here, and then it'll shift back down, and it should hit my 0 point again, because I went when the two of them add together out here, I've got plus 90 and minus 90. That gets me back to 0 there. So it'll look something like that. And that's my combined response for the phase in the blue here. That's my magnitude, and that's the phase for this transfer function that includes a pole and a 0. And then presumably, in real life, this could have been our plant model, and this could have been a lead compensator for as our control algorithm. Okay. Now I can start getting a little more complex systems. Here I have a 0 up here. I have two poles. One of them is at the origin. Poles at the origin are fun. That side. So I can rewrite all this a bit. You notice the numbers here. I've got the S plus 5, 35S plus 35. That's the same as the previous example. So without going, basically we know that our steady state gain, if we had a steady state gain, would be the, what was it? See, I forgot already. 17 dB. which were essentially, we could add 17 dB everywhere, from one side to the other. I could just draw a line here at 17, and that would be one of the things I would add in. Then that just ends up with too many lines. But what I'd also see here is a pole at 0, okay? Now, with that pole at the 0, what's the steady state gain? Well, there really isn't any, because, if we look at this transfer function as s goes to 0, the denominator just goes to infinity, and and that's really what happens with that integrator at the pole. If you give it a constant input, the output just grows and grows and grows and grows. It's 1 over s. It just integrates. So, but what we also know is that, well, let me write this in a better form here. If I have, I can write that as 7 times s plus 7 all over, or I'm not going to write, not s, so let's make this j omega. And I'm deviating from my notes. That's always dangerous. J omega times 1 over 5 j omega plus 5. Okay? If I can factor all that out, I have the 7, which is the 17 dB. I have 1 over j omega times j omega plus 7 times 1 over 1/5 j omega plus, well, that's a 1, plus 1, and I have a 7 times. So I can kind of factor that out into my individual pieces, and that's the way we're going to draw it, of course, is looking at each one, and since in the magnitudes they're all in dB, instead of multiplying, we'll be adding. So I've got my 17 dB, and I have this 1 over j omega term here for the pole right at the origin. At a frequency of 1, I get 1 over 1, right? Times the square root of minus 1, or 1j. So, but the magnitude there is just 1. So this whole, this bare 0 is would normally pass through 0 dB here at a frequency of 1. If I add that 17 dB, which is from that 7 to that, I can say it's going to pass through the 17 dB point right there at a frequency equals 1, and it has our slope of 20 dB per decade, because it's a single pole. So from 17, I go a decade, that's 7, somewhere about there. Why did that erase? So I can connect those as best I can, extrapolate a bit, and that's my 1 over j omega, okay? That's the pole at the origin. I also have the same poles and zeros I had before, so I can say this this pole here, this, oh, that's not 7. Yes, it is a 7. No, it's a 1, because I took 35 outside. That's a 1. That's the problem with doing this by myself. I don't have somebody in the classroom telling me I did it wrong. Where are you guys when I need you? Okay, so I have a pole here, or 0 here at 1. That's right there. It has a slope of 20 dB per decade. It keeps going. And then I have one at 2, 3, 4, 5 with that same slope. Just eyeballing it there. In the phase plot, the phase of a pole at the origin is minus 90, right? If I draw my complex S-plane or J complex plane here. Well, this is the real part. This is the imaginary part. There is no real part to this. So whatever omega is, I'm just marching up the imaginary axis, and that angle is always 90 degrees. Okay? So my pole at the origin gives me a constant 90 degrees of phase. My zero gives me, and I'm just going to roughly sketch this. The zero goes like this, and my pole goes like there, and it goes like that. And I guess my zero should have started up here. I'm sorry. I drew it in the wrong place. Let me erase that. Zero goes like this, and that goes from 0 to plus 90. So I add those together, change colors once again, go back to red. So my initial response at low frequency is just this, till we get to here. Now I have a positive 20 degrees and a 20 dB per decade and a negative 20 dB per decade. So that goes flat up to this point, and where it lines up here. And then now I have my slope of 20 dB per decade down there. So it looks something like that. And in the phase, we can graphically, we start here at minus 90, and it just happens, this goes like that. So we'll start at minus 90, we'll start rising up in parallel till we get to this point. Now I have a pole and a zero coming into play at the same time. That remains pretty constant, and this flattens out there. Constant out to here, and then it comes back down to my initial minus 90, somewhere there about there, and out there. Okay? Bad artwork, but we take each component, add them up independently, or plot them independently, and then graphically add them. And, if you wanted to take the time, we could get the exact values at each of those corners and do a better job, but that doesn't, I don't want to spend a lot of time on this, because you guys have other things to do too, right? I get paid, I can do this all day long. So here's another one where we have a second order transfer function, and it happens here that wait a minute, back up, combination system. Sorry, I skipped the page. I'm looking at my notes, not the slides. Okay, so here we have a second order, really we have 3 poles, and they're all real. I can factor this out to be G of J omega equals 2500 over S times S plus 5, not S, J omegas, J omega, and J omega plus 250. Okay, if I do my magic again, I find out that my steady state gain K equals 10, which it happens to be 20 dB. No surprise there, since we multiply by 20 after take the log 10. Do that one in your head. I have poles at 0, minus 5, and 50. And we're going to do the same kind of thing we did before. We're going to say, I got that pole at 0, so at a frequency of 1, it would go through 0 dB, but since I have this gain of 20 dB, I'm going to put that pole right, make it pass through that 20 dB line just to reduce the number of lines I have to draw. Go 1 decade, and it's 20 dBs per decade, so that's my pole at 0. I have my pole at 5, 2, 3, 4, 5, right there. So that goes here and rolls off at 20 dBs per decade. And that goes to, my line is pretty, because this should really go here, and then this one goes there. Try to draw those, because they're actually parallel here. And then I have the third pole at 50, which is right there. And that one rolls off, again, parallel to those other ones. And it was at 0 here. In our phase diagram, I've got the minus 90 from my 0 at the origin, the pole at the origin, excuse me. I've got a pole that rolls off from, let's see, what are my frequencies here? I got 5. Let me mark those 2, 3, 4, 5, and I've got from here to there. So I've got one that rolls off 90 degrees. From there, it's 45 at that point at the break frequency. Gets to minus 90 out here at 50. That's for the first one. And then it's horizontal here, horizontal there. And then I have the one centered around 50, which starts here, hits 45 at 50, and then hits minus 90 at 500. So that's a straight line there. And it was 0 dBs up here. Change colors. Anybody got a preference? We'll do purple. I haven't done purple. So when we add these up, I start out here at, I've got this going along here. At this point, I've got 20 dB slope there, and I'm adding another 20 dB. So this will roll off at 40 dB, and then when I get to this point, it'll roll off at 60 dBs per decade. And I'm not actually trying to draw that exceptionally accurately, just in the interest of time. Same thing here, we started at minus 90. I rolled down, I'm going to roll down to 45 degrees by there, and from there I'm going to hit, well, at this point I got 90, 180 plus 45. I'm going to go through that point. Then the slope will reduce, and I'll come out, end up there. So I end up with something like that. Okay? Not very well drawn, but that's the concept. We just keep adding these points up. Okay. Now we do the second order. This one has a pair of complex poles, and so what I'm going to do is rewrite that in the form of the natural frequency and damping ratio, because then given the damping ratio and the natural frequency, we know where to put our break frequencies, we know where to put the corner points on the phase plot, we can calculate the peak values. So if I write this out, in the form of omega n squared all over s squared plus 2 zeta omega n plus omega n squared, okay? Well, I can see that omega n squared, I've got 2,500, 2,500, so that works out quite nicely. Gives me omega n of 50. My from 2 zeta omega n, I know 2, I know omega n, don't know zeta, but I know that they all equal to 10, right? So zeta equals 10 over 2 omega n, and that comes out to be 0.1 is my zeta. My gain is 1 because I just have the omega n squared in the numerator and the denominator. And again, I could look at the final value, use the final value theorem. As s goes to 0, as these points go to 0, I'm left with 1. So that'll get me started. Let's start with that. I have my omega n of 50. So that's my break point there. This is omega n. I have a straight line out to here, and then I roll off at 40 dB per decade instead of 20 because I have 2 poles. And I have some kind of peak here, which I haven't calculated yet. I know the frequency of the peak, omega r, equals omega n times the square root of 1 minus 2 zeta squared. And that, in that case, if I plug in the numbers, turn the crank, I get 49.5. And in decibels, that is, oh, no, that's not, that's the frequency, radians per second. I got a step ahead. And the magnitude here at G, J, omega, the maximum, is equal to 1 over 2 zeta times the square root of 1 minus 2 zeta squared. And that comes out to be 5, approximately 5, which is basically 14 decibels. Okay? So I'm going to have a peak at 49.5 radians per second, just the left of that. It's going to be 14 dB, so it's somewhere in there. And I'll just kind of draw in my peak like that. So that's my straight line approximation for the magnitude. For the, I'm going to erase this just because I'm going to need the room. For the phase, it goes through, because there's 2 poles, it's going to go through minus 90 degrees at that break frequency right there. But we know that the slope depends on our damping, and we can calculate the corner frequencies for the phase plot. Basically, our phase, we go the one corner is at 1/5 to the zeta times omega n. In that case, that works out to 42, and the other corner is at 5 to the zeta times omega n, and that is equal to 59. So we go to 42, it's somewhere about here. 59 is somewhere around there. Draw a straight line at 180, straight line at 0, and there's my phase. And I think I covered all of that. Yes, that is my transfer function. Fairly straightforward. We just chunk them together. Now, you ready for some fun? Sure we are. Now, what do we have here? Oh, we got a mess. Let me rewrite that just a little bit. I'm going to say that G of J omega is equal to 1 over j omega, because I'm going to factor this out as I go, times 1 over 200 j omega plus 1. And since I moved that 200, I have to put a 1 over 200 here, times 2500 all over s squared plus 10. Let me rewrite that, plus 10s, not s. Where's my students when I need them? J omega plus 10 j omega plus 2500. And that's the same second order system we had just a slide ago, so we know what that looks like. And my last piece is this 0 up here. I run out of room, so I'll put it here, times s squared plus s plus 25. And I'm going to divide that by 25, so the steady state gain is 1, and since I divided there, I got a times 25 here, okay? So I now have two constant terms. I have a 25 and a 1 over 200, so my steady state gain is basically 25 over 200. Okay, which is, that's 8, right? I've got it written on my notes here somewhere. I can't see it. No, I hate to do, oh, not 8. Gosh, it's 1/8. It's 0.125, and that's equal to minus 18 dB. Okay. I hate it when I get stupid. Okay. Now I've got all these other things here. We have that pole at 0. We have a first order pole here with omega break equal to 200. I've got from my previous example here, I know that I have a omega n equal to, what was that equal to? 50. And a zeta equal to 0.1. And then for this 0 here, I have it turns out to be that the omega n equals 5, square root of 5. Where am I going to write this? Omega n equals 5, and zeta equals 0.1 again. Okay, that's for this term there. My pole, or 0, excuse me. So I think I have everything I need to do my approximations. Oh, for those, for the pole, let's see. Yeah, let's look at the 0. I said that omega n equals 5, zeta equals 0.1. I have omega r equals to 4.95 from using the equation from the previous one, which is omega n times the square root of 1 minus 2 zeta squared. And my magnitude there, because my damping is 0.1, it's the same. That magnitude is the peak is equal to 14 decibels. And the pole, complex pole, second order pole, the same numbers as before. We had, omega n equals 50, zeta equals 1. The peak, since that's just a function of zeta and not omega n, is again 14 dB, and omega r we said was 48 point something, 49.5. Okay, so those are the things I need, and I'm going to go to the next slide, so you're going to have to remember all those, right? And what we'll do, I'm not going to draw each and every piece on here because it just turned into a mess. I'm going to start from the left, and I'm going to try to kind of go piece by piece. We have that pole at the origin, so we know we start out with a slope of minus 20 dB per decade, and it's going to go through our minus 18 decibels at omega equals 1. So there's minus 18, and like this, with a slope of 20 dB per decade, okay? That's going to keep going until the first thing that I hit, the next frequency that I hit is my 0, which had a natural frequency of 5, so that's right here. At that point, I'm going to make a turn, so I'm going to continue this down. It should go to, it'll hit about here. Oh, sorry. I leaned on my screen in the wrong spot, trying to steady my hand. So that'll go there. When I get to this peak, now I'm adding a 0, so the 0 has a slope of 20 dB per decade up. That cancels the slope of the 20 dB from the pole. So I end up with a, no, it does not. It's a complex 0. It has a slope of 40 dB per decade up, because there's two poles there. It's complex. And so 40 dB minus 20 leaves me with a 20 dB increase here. And I'm just not even going to try and draw this to scale. And I also know I have my peak of that 14 dB, and it's just a little bit to the left, and it's going to go like that. So now this is a plus 20. I get to my next one at 50 is my next corner frequency. So I'll go up there till I hit 50. I'm not guaranteeing accuracy. And now I have plus 20 slope, and I'm going to add two poles. So 20 plus negative 40 is a negative 20. So I'm going to roll off at negative 20 until I get to 200, right there. And I have that peak. And at 200, try to steady my hand and hit that sensor. At 200, I roll off at 40 dB per decade because I'm adding another pole. Okay, and that's probably too steep the way I drew it there. Okay, so that is the magnitude, and I just kind of started at one end and added them up. The phase, I have minus 90. That continues over. My corner frequencies for that first 0 were at 42, somewhere about here, and it went 45 degrees. No, it's complex. There's two of them, so it goes a total of 90 degrees. So at 0 degrees at 5, and the other corner was there. The phase is going to go up like this, and it's going to get I'm going to draw the next, and it flattens out. I'm going to draw the effect of the complex pole and the first order pole separately because they kind of overlap. So if I'm going to draw a dotted line here out to 42, that's right there. And that passes through here and there, and that would be the effect of that complex pole. And I have my my zero here, I'll just draw it up here. I'm going to change colors, because otherwise it's going to get too confusing. My zero, my last pole has a phase that goes from 0 to minus 90. It passes through 45 right there, if I was just to draw it by itself, and then it goes to minus 90 somewhere out here, and it goes to, starts at 1/10 of that, so it starts at 20, so it starts here. I'm going to draw this as a dotted line. So that's the final pole. So what I have happening here, now let's go to color number 3. Green. I haven't used green yet, have I? So here I have this constant going this way and that slope going that way. So this is going to come along and it's going to start sagging down, and we get to this point, we essentially add that effect of that complex pole right there, so that goes down like that, and then this continues down parallel to this 0 until it gets out to here, and then it will go flat. So we just kind of worked our way from left to right, adding these poles and zeros as they happened, and we end up with an ugly drawing because I didn't spend a lot of time measuring points, because that's not the point, right? The point is just to illustrate the process and not to waste your time. And there's, putting it into MATLAB, you can see much the same thing, where the 0 is here, that complex, the pole at the origin is this, the effect of the complex pole here switches it up 20 degrees, there's our peak, we get another peak here, and we go, this is 20, this is 20 up, this is 20 down, and right in here, it's kind of hard to see the change, but now we're at 40 dBs per decade that last. Okay? Because, they're not the sharp corners that they are when you draw them by hand. And the phase started at minus 90. We hit that complex 0. It started to head up to 180 degrees from minus 90 to plus 90. Doesn't quite get there because I have this, I have two things. I have this pole and that pole over here. That pole, it's not a pole, I circled my thing. Those two poles happening, and you can see it kind of starts to roll off there, hits the next complex pole, jumps down, and then keeps rolling off into infinity and beyond. So that's how the drawing looks in MATLAB. That's the last slide. I want to do this, just give you some concrete examples. I, hope you kind of played along. If you didn't, you go back and replay some of those and see what you got. And we'll talk to you next time.